What is an exponential function and how do you graph one? Remember, the title of your notes should be exponential functions. And we are going to look at some examples of what an exponential function is and how you can graph one. And we'll be able to answer this question by the end of the video. Here's an example of how your notes should be set up to take notes from this video. There is no video titled 2 or 3, there's just the 1. Remember, there should be a section and title up top. You can get that from your outline or from the website. And then you have your summary that should be 3 to 4 sentences in length. Okay, let's go ahead and contrast, or let's go ahead and look at the differences between two types of functions. Remember that we had discussed function and function notation. And so function notation would be something like f of x. You know, it can even be g of x or h of x. Well, let's go ahead and compare the two. We talked about linear functions, and remember, linear functions change at a constant rate. They also have a rate of change, which is their slope, and it is also constant. Now, exponential functions are going to change at a changing rate, and we're going to take a look at an example of how something can change at a changing rate when we meet in class. And also, the change is at a constant percent rate. Okay, and this percent rate is going to be huge. Just like the rate of change, the slope is huge. So is the change at a constant percent rate. Okay, let's continue our comparison of a linear function and an exponential function. Suppose you have a choice of two different jobs at after graduation, not at graduation, but after graduation. One job is going to start you at $30,000 with a 6% per year increase. And we'll take a look at some examples as what does the data look like for this example. So $30,000 with a 6% year increase. That means that if this is my dollar amount that I'm making for 1 year, I will get 6% of that added onto this amount. And that's going to happen each year. Or I can start a job that's $10,000 more, and each year I'm going to make $1,200 per year. So each year, no matter what my starting cost is, I'm just going to add an extra $1,200 or an extra $1,200 onto that total. So, which should you choose? One is a linear growth and one is an exponential growth. Out of these situations, let's label the first one as 1 and the second one as 2. Which one do you think is linear growth? And which one do you think is exponential growth? Take a minute and try to decide. Remember that linear growth is going to have a constant rate of change, and the exponential growth is going to have a rate that changes over time. So once again, let's look at option A and option B. Remember, option A is going to give you a percent increase each year. Excuse me, let me show you. Option A here is going to give you a percent increase each year, 6% increase each year. And then option B is going to give you $1,200 each year. So once again, which one is better? And remember, how do you get to each next value for option A? So for option A, this is my starting cost. I get 6% of that, and then I added that onto my total. Then I get 6% of this number, and that's added on to, and then I'm given this total. And then 6% of that number. So notice each time I do the 6%, I'm taking 6% of a larger number. And for option B, I just keep adding $1,200, adding $1,200, adding $1,200, no matter how much I'm making in the previous years. So once again, let's take a look. When is option A better? So if you keep looking at your data here, option A starts to get better around 11 years. In 11 years, you're actually going to start making more money than option B. And when is option B better? Well, up to 11 years, option B seems to be the best choice. So maybe you would want to keep option B, have that salary pay at 10 years, and then try to switch over saying that's how much you want to make at your new job, option A, and then you'll start to get that 6% increase, and it will be a much better for you in the long run. So remember, for option B, we had a rate increase at a constant 1,200% or $1,200. And for option A, the rate of increase is changing. The percent of increase is a constant though. So the ratio of successive years is 1.06. This is the number that we really that we use to multiply to each value to get to the next one. So now you're probably wondering which one is linear and which one is exponential. Well, since we have this constant rate of change, this 1200 is going to be linear. So this is, there's an E and then an A. This is going to be option B. And then for option A, this is going to be our exponential one. So hopefully you got that right. If you didn't, then we're going to discuss in class why one is linear and why one is exponential. Please excuse my voice a little bit if you can hear that I'm sick, so my nose is really stuffed up. But hopefully you can understand me. Let's look at a second example. Before we compare two jobs that pay different wages each year, and now we're going to consider a savings account. Once you are old enough to open up your banking account, you want to have the savings account. And this one is compounded annually. And we're actually going to be able to do this later on after we discuss this entire week using exponential functions. So this is compounded yearly. So you have $100 in your account and you're going to receive a 5% annual interest. So let's take a look at this chart that they give us to understand this information. At the end of year 1, you have $100 you put in. We're going to give a 5%. This is a decimal for 5%, a 5% increase. So $5, and that's added on to your total amount, which was $100 that you put in. So now your new balance is $105. So in 1 year, you made $5 free dollars, $5 extra bucks. So it's always nice to be compounded yearly for a savings account. This is why people have savings account. They're able to put money away and then make money off of that money that they have stored. At the end of year 2, we then take this new balance that comes over here and we multiply it by that rate, which is 5%. And then we get this new dollar amount, which is $5.25. And now that's added on to this one here. And you get $110.25. This is called compounded and yearly. Each year, it's just adding on a new balance, but based on what you previously have. So now you take this amount. For year 3, you multiply it by the 5%. You make $5.51 and you add that to the previous amount and you get year 3. On your own, try to get year 4 and year 5. The same way that we did year 1, 2, and 3. And now that you tried to do 4 and 5, you can check your answers here. Here's year 4 and year 5. And now look at, after 10 years, you put in $100 into your savings account. After 10 years, you now have $162.89. So you made $62.89 increase over 10 years. And this money right here is that free money. What if you were using a calculator? Sometimes you can use a calculator, a graphing calculator, and it makes it much easier than having to graph this information on your own. So here are some examples of here's a graphic calculator. This is the Y equals screen, and so we're taking the $100 you put in, and we're going to multiply that by the 105, and the X is based on the different year amount. So here it is, and we can see at 5 years, if we look on the graph, we have $127.63 in our account. If you check the table that you should have written down, you can see that that is also correct. So there's 2 ways to verify. It was actually filling out the table ourselves, or you can set it up in your calculator so that you can graph it and get the table and the values that you need. Exponential functions can be used to do exponential modeling, and this is based off of real-world data. For example, population growth is often modeled by exponential functions. We can't use a linear function to show the growth of a population. We must use exponential functions. The half-life of radioactive materials, so really just the life of the radioactive material, which actually comes down to the term called half-life, can be modeled by exponential functions. So this is an example. Population growth is an example of growth with exponential modeling, and then the half-life of radioactive materials can be seen as decay. And we're going to go ahead and do growth and decay, not this week, but next week. Okay, let's think back to what we discussed. We want to recall the formula that we use for the growth factor of the exponential modeling, and this is on the savings account. We had the new balance equals the old balance plus 0.05 plus the old balance. So another way of writing the formula would be new balance is equal to 1 plus 0.5 instead of just 0.5. This 1 is that old balance plus what is being added, the percentage, and we still multiply that by the old balance. I want you to think about, why are these equivalent? Why is this one equivalent to this one? And that's because of this growth factor. This growth factor is just 1 plus the interest rate as a fraction. We discussed 2 examples of growth, and now we're going to look at a decreasing exponential. We can consider a medication. A patient takes 100 milligrams. Once it is taken, the body filters medication out over a period of time, which is why you have to wait a certain time before you take another dose of the medication. Suppose it removes 15% of what is present in the bloodstream every hour. So here's our table. At first we have 100 milligrams, and we're going to take away 15% of that and times it by 100, and that's going to give us the 85. Then we're going to take 85 now, and we're going to subtract it by 15% of the 85, and then we'll get 72.25. And we're going to keep doing that. Now we'll take 72.25 and subtract 15% of that amount, and that's going to give us our new amount. And so after we do this for a while, we can figure out how many hours it takes for the medication to go through the bloodstream. And then you can go ahead and make instructions on letting the patient know how long they must wait till they take the medication again. Okay, so we were wondering, how do we graph this data? Now, we can use a graphing calculator as we saw in a previous example, but we could also, oops, I realized that you can't see the D. So this is decreasing exponentials. One way is using a graphic calculator, one way is to do it yourself. So if you finish filling out your chart, which you should have done, you will see that after the 7th hour, you have 32.06 milligrams of medication remaining in your bloodstream. And we can use a graph. Here we're going by we start at 100 because that's what we start with, and we see the amounts coming down from there. And then these are the hours, and here's our exponential graph. Notice this is different than a linear graph. I can't connect the dots with a straight line. Instead, they're slowly, gradually decreasing over time. And this amount is decreasing in different each time that we're going down, which is why it's not a linear function. So that answers your question of this video. What is an exponential function, and how do you graph one? You can graph one by creating a chart and then plotting the points on a graph. Now, in my head, I'm still thinking, when is that medication out of my system? Or when is it less than, let's look at this example, when is it less than 5 milligrams? Because once it's less than 5 milligrams, then I know I can maybe start getting ready to take the medication again. So we're going to be solving an exponential equation graphically. Here we graph that entire equation, and I listed it, here it is listed out. We used a graphing calculator for this example, because remember, we only went up to the 7th hour. And this shows us that if we want to know the y, and that's how much is left, about 5 milligrams, we are going to have to be at x, which is going to be 18 hours. So after 18 hours, we could be at about 5 milligrams. And this is a function that models what we're talking about. Remember, we started off with 100 milligrams of medication. We take 85% of what it is left, and the t is going to represent time. Okay, so that's 1 hour or 2 hour or 3 hour. And we want to know, when is this function going to be less than 5? And that is right here for this case, 18. Now that we discussed exponential functions, I've given you an introduction into how to understand them. I've shown you how to graph one using a table and a graph, and we looked at the equation that we would use. So here is the actual information that you need for your notes, along with everything else we covered. All exponential functions have the general format of f of t equals a times b to the t power, and t is time. So we're going to always keep it as t instead of using x, but you could use x as well. Instead of f of t, you could write f of x equals a times b to the x power. So a is the initial value. Okay, that's what you start with. So we started with 100 milligrams of medication, or you can start with $100 in your bank account. Here's your growth factor. You can increase 6% over some time, or you can decrease 85% over time. And t is the number of time periods. Okay, so it could be 1 week, 2 week, 3 week, or 1 hour, 2 hour, 3 hour, or even years. So make sure that you have this written in your notes, box it, draw arrows to it, star it, highlight it, whatever you need to do to know that this is very, very important formula. And now for our final slide, before we actually go back to the original question, I just want to show you what happens when the b is greater than 1. Notice the direction of your graph would be increasing, and when b is less than 1, you are decreasing on the graph. And when it says to create a spreadsheet, that means to take this information and put it into a table. We'll be practicing these concepts over again in class. Make sure to bring all your questions. So now, once again, think about what is an exponential function and how do you graph one. Think about what it is and how you graph it, and explain the process to me. Explain in detail what the exponential function is used for and what is its percent rate. And then how do you graph one? Explain to me how do you graph one, and do this in your summary.